Okay, hi everyone. This lesson is on solving exponential equations using logarithms. So we've used this, we've built up to this lesson right here where we're going to actually apply our understanding of logarithms to help us actually solve some of these equations. So it says solve the following using three different methods. 2 to the power of x equals 7. I'm always going to try to get a common base. But if you take a look at this right here, 2, I can't rewrite with any bases because 2 is prime and 7 is also prime. So getting a common base here is not going to work. So this is where we're going to use our logs to help us out eventually. But for right now, let's do some trial and error. So that's one option that we always have, and that's what we've been using up until this point. Okay, so 2 to the power of x equals 7. What I'm going to do here is I'm going to go to my calculator and I'm just going to guess and check until I can get values that work. So I already know that 2 squared is going to be 4. And I know that 2 cubed is going to be 8. So because I'm trying to get a number to be equal to 7, I know that my answer is going to be somewhere in between 2 and 3. So maybe I'll try 2 to the power of 2.5. This number is too small, so we will try something bigger than that. So maybe 2 to the power of 2.7. And if you look right here, this number is getting closer to that 7. So I'll try 2 to the power of 2.9. That number's too big. So then I'll try maybe 2.8. And if you look right here, this is getting pretty close to 7. So maybe like 8.85. This is too big. So maybe I'll do like 0.82. It's still a little bit too big. Let's try 0.81. It's still a little bit too big, but we knew that 2.8 is too small. So like I would do 2.805. And then I would just keep going and going and going until I find a value that works. For trial and error, 2.81 is a pretty good test, right? Like it's a pretty good approximation right here. So that's one option, not the most efficient option, okay? So the second option is to rewrite this in log form. So if I've got 2 to the power of x equals 7, we could say that x, the exponent, is equal to log base 2 of 7. And then there's a change of base formula that's going to be helpful to us. And that's going to say that log base a of b is equal to log base c of b over log base c of a. And here, honestly, these c's could be any base that you want. It really doesn't matter. So for example, right here, but what does matter is that this b right here has to go in the numerator and this a has to go in the denominator. So actually what I can do here is I can write this out as log of 7 over log of 2, where the c in this example would be like an invisible 10. You can use any base you want. Typically, we use 10 because it's just the easiest one to do. Some of you have this option in your calculator to begin with, where you can literally just type in log base 2 of 7. We only use the change of base formula if we don't have that option. So for example, here in my calculator, I don't have that option. Like if I tried to do log right here, it doesn't give me any options for bases. So it's automatically assumed that it's going to be base 10. So I'm going to do log of 7 divided by log of 2. And then this gives me my answer right here, which is approximately 2.81. Okay, and then we have one more option, which is to log both sides. And, and let's write here on option number 2, we'll say that this is changed to log form. So here's option 2. Option 1 is trial and error. And then option 3 is to log both sides. So let's write this out. So 2 to the power of x equals 7. I'm going to log both sides right here. So I'm going to log both sides. So I'm going to say log of 2 to the power of x is going to equal the log of 7. And then after you do that right here, we know that we are actually allowed to bring this x out in front. So I can bring this x out in front right here and say that this is x log of 2 equals log of 7. And then to isolate that x, we just divide log of 7 by log of 2, which gives us the same answer of 2.81. Again, you can use any base you want. We use base 10 because it's just easier, but you can use whatever base you want. If you're going to use just the log button in your calculator, it's going to be base 10. Okay, cool. So now we have another tool in our toolbox to solve exponential equations, but we only do it if we have to, right? Sometimes we have to, sometimes we don't have to. So for example, right here, 8 to the power of x equals the cube root of 16. I'm always going to try to find a common base first. And if I can't find a common base, then I'll go to my logs. And 8 and 16 both can get a common base of 2. So I'm going to rewrite this as 2 to the power of 3. That's what 8 is, okay? And that's being raised to the power of x. And then that's going to equal the cube root of, and then we also know that 16 is 2 to the power of 4. Well, right here, this ends up becoming 2 to the power of 3x equals 2 to the power of 4. And then this is being raised to the power of 1/3 because that's what the cube root means. So then this is 2 to the power of 3x equals 2 to the power of 4 over 3, because when you multiply, because when you have a power to a power, you can just multiply exponents. And now I can set my exponents equal to each other. Divide both sides by 3, which is the same thing as multiplying by 1/3. So x is exactly 4 over 9. I did not need logs to solve this here, okay? But let's take a look at question B. So question B, 5 is just 5. There's nothing else I can do with it. But the number 100, I cannot write this as a base of 5 because 5 to the power of 1 is 5, 5 to the power of 2 is 25, and then 5 to the power of 3 is 125. There's no way that I can get 100 with a base of 5. That's not a nice, even, pretty number. So here I will have to do one of our options that we have up here. Okay, trial and error, I'm going to pass on that one. No thanks. I could either write this in log form or I could log both sides. I'm going to log both sides for this example here, just so you can kind of see what this looks like. I'm going to do a little bit of each throughout this lesson so that way you can see how we have a bunch of different options in our toolbox, okay? So now I can bring this x out in front right here. So this would turn into x times the log of 5 equals the log of 100. And then to isolate x, I would divide log of 100 by log of 5. Type that into my calculator, and I get approximately. So here I'll put in log of 100, which interestingly enough gives me a perfect, nice, even number, because remember, log of 100 is going to have to be 2 because 10 to the power of 2 is 100. But then once I divide that by the log of 5, it's not nice and pretty anymore. So I get approximately 2.86. So here I can say it's about 2.86. Okay, cool. Let's take a look at the next example that we have here. I'm going to try to get a common base, but here my base is 3 and here this is 25. There's just no way I can get that. I'll get rid of the 2 first and see if that helps me by dividing by 2. But when I divide 25 by 2, I get 12.5, and 12.5 also can't be written with a base of 3. So I'm going to try to put this in log form. So remember, the exponent, which is x minus 4, is going to be equal to log base 3, the base right here, of 12.5. So then to isolate x, I'm going to do log base 3 of 12.5 plus 4. and then I will type that into my calculator. If you're lucky enough to have the base, the option to type in log base 3 of 12.5 into your calculator, great. I'm not lucky enough. So I'm going to type in that this is going to be log of 12.5, and then divide that by log of 3 because I'm using the change of base formula. And then I'm going to add 4 to that. And then this is my answer right here, which is approximately 6.30. Okay, and question D right here, I'm going to isolate this 5 to the power of x by adding 1 first, and then dividing by 4, and I end up getting 24. And 5 and 24, there's no way I can write them as a common base, so I have to use logs. So I'm going to use log form again for this right here. So I'm going to say x equals log base 5 of 24, and then I'm going to type that into my calculator. Again, I don't have the option to type in log base 5 of 24, so I'm going to use my change of base formula, which is going to be log of 24 over log of 5. And so my answer here is about 1.97. Okay, and question E. Again, if I can get a common base first, I'm going to try that before I apply logs. And if you remember right here, we can rewrite 4 to the power of x plus 3 as 4 to the power of x times 4 to the power of 3. And then I'll copy the rest of this equation down. And then if you take a look at this right here, I've got a 4 to the power of x in common with both of these. So I'm going to actually factor that out first. When I factor it out of 4 to the power of x times 4 to the power of 3, I get 4 to the power of 3 left over. And then when I factor it out of 4 to the power of x, I get a 1. And then if I go through and I evaluate this, 4 to the power of 3 is 64. 64 minus 1 is 63. I can divide out that 63. And then what exponent do I put on 4 to get 1? It would be 0. So my answer here is 0. So this is what we did previously a few lessons ago. Okay, and then in this last example right here, again, I'm only going to use logs if I absolutely have to. And I see here that I've got 2 to the power of x right here. So I think u substitution is going to be helpful to me, because now I can say, well, this is u squared. And then I've got minus 5 times another u, and then plus 4 equals 0. I can factor and solve and say that u equals 4 or u equals 1. But I don't want to know what u is. I want to know what x is. So now I have to take what u is and sub it in. So this is going to go in here as 2 to the power of x equals 4. And it's also going to go in right here as 2 to the power of x equals 1. So then this right here would have to be 2, and this would have to be 0. Okay, so now we're going to put everything together. We're going to put together what we know about exponential functions, word problems, and then we're going to use logs now to help us solve these equations here. So in example 2, it says a city has a population of 10,000 and it's increasing by 3% per year. How long will it take for the population to double? So we need to have a let statement for the time. So we're going to say let the time equal x, and the time is measured in years. Okay, and if you remember, the general equation for population growth is going to be a times b to the power of x. But just a reminder that b is 1 plus r, and here our r is 3%, so our b is 1.03. So here, this, and then our initial amount is 10,000. This tells us our initial amount is 10,000. So we can say here, f of x equals 10,000 times 1.03 to the power of x. And then it's asking, well, how long will it take for the population to double? Well, if the population doubles, I need the population to be 20,000. So I'm going to sub in 20,000 for f of x. And then here, all I need to do is divide everything by 1,000. So I get 2 equals 1.03 to the power of x. So I'm going to log both sides now to make things easier for me. So now it's going to say log of 2 equals, I can bring this x out in front, x log of 1.03. And then to isolate for x right here, I can say x equals log of 2 over log of 1.03. And then I can type that into my calculator and I would get my answer. And if you see here, I get approximately 23 years, 23 and a half years. All right, in example 3, it says the half-life of a substance is 40 years. How long will it take for 100 grams to decay to 1 gram? So remember, if we have half-lives right here, this is the general equation right here. We know that m sub 0 is going to be 100 grams. We know that the half-life is 40 years, and we want it to decay to 1 gram. So this is what m is going to be. So here, I'm going to replace this m with 1. I know that the initial amount that I'm going to put in here is 100. This is going to be to the power of 1 over 2. This is going to be multiplied by 1 over 2 to the power of t over the h value, which is 40. So I'm going to go through and isolate this piece right here. So how do I do that? I divide everything by 100. So I get 1 over 100 equals 1/2 to the power of t over 40. Now I'm going to write this in log form. So the exponent is equal to log base 1/2 of 1 over 100. But now I need to isolate this t, so I have to multiply everything by 40. So t equals 40 log base 1/2 of 1 over 100. And I'm going to use the Desmos graphing calculator because I can do bases in the Desmos graphing calculator. So let's go ahead and type this out. So 40 times the log with base 1/2 of 1 over 100. And my answer right here is about 266 years. Okay, example 4 is a little bit trickier. This time it says a sample of radioactive material had a mass of 56.8 grams. So this is m sub 0. After 5 years, the material decayed to 20.5 grams. This is m. Now it says to determine the half-life of the substance. So we're still going to use our general equation here. And then after 5 years is the time. Okay, so I'm going to sub in all the information here. So I know that m is going to be 20.5. I know that m sub 0, the initial amount, is going to be 56.8. This is going to be multiplied by 1/2 to the power of 5. And it's 5 because I know that the t is 5 over h. And now we need to solve for this h in this exponent right here. So the first thing I'm going to do is divide everything by 56.8. And 20.5 doesn't get divided by 56.8 evenly, but if I were to reduce that fraction, it would end up becoming 205 over 568, and that's going to be 1/2 to the power of 5 over h. Now I'm going to, this time I'm going to decide to log both sides, so I'm going to log on this side and I'm going to log on this side. So now I know right here that this is going to be the log of 205 over 568 is going to equal 5 over h times the log of 1/2. Next thing I'm going to do is isolate this 5 over h right here. So how am I going to do that? Divide everything by log of 1/2. So here I'm going to say log of 205 over 568 over the log of 1/2 is going to equal 5 over h. Well, here's where things get a little bit trickier because I don't love the fact that this h is in the denominator here. So I'm going to multiply everything by h. So this will now say h times the log of 205 over 568 over the log of 1/2 is going to equal 5. And then in order for me to be able to isolate h, I need to divide by all of this stuff right here. But when you divide by all of this stuff, it's the same thing as multiplying by the reciprocal. So this would become 5 times the log of 1/2 all over the log of 205 over 568. So let's go ahead and type that into our calculator and see what we get, and this will tell us approximately how long our half-life is. So here our half-life is approximately 3.4 years, but I'm going to say h equals so we can kind of verify to make sure that this works. So I'm going to test this to see if this is right. We know that we started with 56.8 grams, and then I'm going to multiply that by 1/2 to the power of 5 over our half-life, which I called h right here. And I truly have 20.5 grams left. So therefore, your half-life is approximately 3.4 years. And that's it for this video. Let me